Module 2, Fields and Currents. 2.1 Electrostatic fields from charge distributions. Electrostatics is the study of electric fields produced by stationary charges. Charges may be distributed in different ways, as point charges, along lines, across surfaces, or throughout a volume. A single point charge produces an electric field radiating outward. A line of charges produces a cylindrical symmetry in its field. A charged surface produces a uniform field near the surface. A volume charge distribution produces a more complex field pattern. The strength of the field depends on both the amount of charge and the geometry of the distribution. These fields explain phenomena such as capacitance and energy storage in electric fields. 2.2 Magnetic fields around conductors. Whenever current flows through a conductor, it produces a surrounding magnetic field. For a long straight conductor, the magnetic field forms concentric circles around the wire. For a coil or solenoid, the field becomes stronger and more uniform inside the coil, resembling the field of a bar magnet. This principle is central to electromagnets, transformers, and motors. Engineers often design conductor arrangements to shape magnetic fields for desired applications. 2.3 Time-varying magnetic and electric fields. When electric or magnetic fields vary with time, new interactions emerge. A time-varying magnetic field induces an electric field, as described by Faraday's law. A time-varying electric field produces a magnetic field, extending Ampere's law through the displacement current concept. These dynamic interactions give rise to electromagnetic waves, which propagate through space carrying energy. This discovery, pioneered by James Clerk Maxwell, unified electricity and magnetism into a single electromagnetic theory. 2.4 Conduction current. Conduction current is the familiar current that results from the motion of electric charges, typically electrons, through a conductor under the influence of an electric field. It is governed by material properties such as conductivity and resistance. This current is what powers our devices and lights our homes. 2.5 Displacement current. Displacement current, introduced by Maxwell, is not an actual movement of charge but a term that accounts for the changing electric field in time. For example, in a capacitor, even though there is no physical charge crossing the dielectric, the changing electric field creates an effect equivalent to a current. The concept of displacement current was revolutionary because it completed Ampere's law and made it consistent with charge conservation. More importantly, it predicted the existence of electromagnetic waves, oscillations of electric and magnetic fields that can travel through empty space. 2.6 Linking it all together. At this point, we can see the logical progression. Stationary charges create electric fields. Moving charges, or currents, create magnetic fields. Time-varying magnetic fields create electric fields. Time-varying electric fields create magnetic fields. This elegant symmetry leads to Maxwell's equations, the foundation of electromagnetics, which we will explore further in advanced courses. For now, the focus is on appreciating how each law connects to the others, forming a complete picture of field interactions. In this module, we explored how charges and currents generate fields, both static and time-varying. We saw how conduction currents and displacement currents combine to preserve consistency in Maxwell's framework. Most importantly, we discovered that the interplay of time-varying electric and magnetic fields is what gives rise to electromagnetic waves, enabling wireless communication, radio, and modern technology. Course conclusion. We have now completed the course Electromagnetic Fields and Waves I. In Module 1, we studied vector analysis tools, integral theorems, and fundamental laws like Ampere's and Faraday's. In Module 2, we applied these principles to real physical systems, charges, conductors, currents, and time-varying fields. We also understood the critical distinction between conduction current and displacement current. This course has laid a strong foundation for understanding how electricity and magnetism interconnect, leading ultimately to electromagnetic waves. As you continue into more advanced courses, you will study how these waves propagate, interact with materials, and form the basis for all modern communication and energy systems.